My name is Robert Birch, and on behalf of my team, Professor Ekwe, Dr. Birch, Ms. Regis, Ms. Steele, and Mr. Harris, I'm presenting the topic crack propagation and fracture in two Trinidadian soils under varying peat content during constant tensile tests. This research focuses on tillage and tensile fracture in tillage activities. Tillage is known as an essential agricultural activity, and it uses large amounts of energy to create an environment that can sustain plant growth. Such an environment involves the pulverization of soil so that you get good filtration of air, adequate drainage, and root development. Many authors have investigated the activity of tillage and have found that as the soil and tool interact each other at the boundary, stress fields are created that result in the deformation, yielding, and fracture of the soil, leading to the breakup and displacement of the soil. Some of these authors have indicated that the mechanism of failure can be described either as shear failure, tensile failure, bending failure, or crescent failure. Our focus will be on tensile failure. Tensile fracture and crack propagation is a failure mechanism in soils that can lead to crack propagation and loosening and fragmentation of soil matrix. It has application, as said, in the pulverization of soil during tillage operations, as well as the harvesting of root crops, or in landslips. We have found through literature that a lot of work has been done on shear failure, flow failure, and tensile failure. However, there has been very little work on the mechanism of soil loosening and fracture in tensile failure with respect to the incorporation of organic matter. So our focus will be on tensile failure with the incorporation of organic matter. We believe that this work would allow us to improve the design of appropriate tools and improve soil management practices so that can lead to soil conservation and improve energy utilization during tillage. We turn to some work that has been done by Hallett and Houston 2005 and Carmichael 2005. Their work has been able to identify 4 stages during the fracture process. These 4 stages is described on the right-hand side: elastic deformation or yielding. Then the second stage of plastic deformation at the crack tip. Third stage, the creation of new surfaces and rapid crack growth. And a fourth stage of steady state growth leading to plastic failure. We were able now to take a fundamental equation that describes crack propagation, which says that the input energy is equal to the elastic energy plus the kinetic energy plus the plastic energy plus the energy needed to create surfaces. By modification, and we were able to develop an equation on your left-hand side which states that pi dot, the input energy per unit time, is equal to phi mass compliance times the acceleration component by the velocity component plus 2 gamma, which is a property of the material, times the rate of crack growth. But our focus this evening is on crack growth under constant tensile loading. And to do this, the velocity component will be constant, thereby the acceleration component tends to 0, and the equation it becomes pi dot is equal to 2 gamma A dot. Our aim is to determine the initial energy that is required to form the crack and the relationship with the initial condition of the soil. Further, we want to determine the crack growth and its relationship with the initial condition of the soil. We design an experiment at a compaction level of 404 kilopascals. We use 404 because it relates to real life field conditions. And the experimental design used a 2x4x4x4 design where we use two soils, two different types of soils, Piarco, sandy, loam, and Talparo. These soils have been researched before. 4 levels of peat content at 0, 4, 8, and 12%. 4 levels of water status at the plastic limit. It represents when the soil is wet. And then 5% less, 10% less, and 15% less the plastic limit. 15% less representing the driest condition of the soil. Our test will be repeated 4 times. In this figure, we see the experimental setup. We have a camera that is used to videotape the process of fracture. And afterwards, we downloaded the video and used the images to actually measure the rate of crack growth. We have a test mold that was modified and that has the test mold itself has 2 components. One is a stationary part and one is a moving part. The moving part is attached to the LVDT. And then we have a constant load using a pulley system. At the beginning of the experiment, the moving part will slide and the LVDT will take the measurement of the formation with respect to time. Here I'm presenting some results. We have different factors levels, soil type, peat added, and water states, all representing the initial conditions of the soil. And we will measure the time to fracture, initial resilience, and crack growth per unit thickness. We see here under soil type that Talparo has a higher time to fracture than Piarco. Crack growth, Talparo has a higher crack growth than Piarco. But the initial resilience, Talparo has a lower initial resilience than Talparo, but the difference between the means is not significant. When we look under percent peat, we see that as we add peat, there's an increase in time to fracture, but there's significance between the means between 0 and 12%. We also see that when we add peat, that the crack growth decreases, but the major difference is between 0% peat and 12% peat. For water states, as we add water, we move from a drier soil to a wet soil, we see that the time to fracture actually increases. We looked at also interaction of factors, and in this graph here, we have the failure time versus peat added and type of soil.
Sorry, Mr. Birch, you have 1 minute, ma'am.
Okay, type of soil. You see there at 0% peat, there's not much significance difference between the means, but as we add peat, there's much significance. When we look at crack growth, we see that at the increase in water content, there's a decrease in crack growth. Also, we see that the 0% peat has the largest crack growth. When we look at crack growth for particular soils, we see again that at 0% peat, we have a high crack growth. And our conclusions are Talparo propagates cracks faster than Piarco at 0% peat. Peat inhibits the crack growth, especially with Talparo soil. We believe that peat may be a stabilizing agent in conjunction with clay particles to resist failure due to creep. The time to failure for both soils increase with increasing percent peat and water. Soils fails faster without peat than soils with peat under constant loading. And soils took longer to propagate cracks at the plastic limit, and therefore soils at the plastic limit do not present an ideal condition for pulverization. Thank you.
Okay. Thank you for the presentation. We welcome questions from presenters.
Okay. Are there no questions as yet? Okay, so we have one question. It's from, who is this from? It says, very good work. How was the moisture content in the soil controlled such that the soil could be considered homogeneous? That's the first part of it. You wish to respond? Then we'll do the second part.
Sure. That's the thing. All right. I think there are two questions there. We did control the moisture content in the soil, but soil cannot really be considered homogeneous. How we control the moisture content was based on the methodology that we use, where we prepare the soil, we allowed it to set for over 24 hours. Then we prepare the moulds. Our testing took over a 4-hour period. Longer than that, the soil tends to dry, right? And we had a experience in a controlled environment.
The second part of the, well, I don't know.
The homogeneous part. The homogeneous part. So, is very, all right, to say that soil is homogeneous is a very difficult statement, right? But what we did to ensure that there was no effects in terms of, or the minimal changes, is that the process, we did a large sample of soil, mixed it together, and we bagged that. And we left that for 24 hours before we engaged the experiment itself. So we allowed the soil to settle.
Okay, so here's a second part to his question. How will this work directly impact farmers in terms of maintenance and other costs?
Right. So this part of the work is just one of many. We did creep tests, we did dynamic testing and so on. But for this part of the work, when we look at creep testing, you will see that soils that are drier tend to crack faster with no peat under constant load. So if, for instance, you had a situation on a soil, you will till in the soil on a or you on a hilly slope, right? But you want to engage tillage, right? You will tend to want to have this operation occurring when the soil is dry and not when the soil is wet, right? When the soil is wet, you will tend to use more energy, right? And then you will not get the type of pulverization that you will want.
Okay. Any more questions?
What's the effect of the peat on the two soils?
What's the effects of the peat on?
On the two soils.
Okay. Peat seems to have a more effect on the Talparo soil than the Piarco soil, right? We saw that by engaging peat, or by using peat, that there was a drastic reduction in the crack growth, right? Whereas with the Piarco soil, right, if you add minimal peat to Talparo, you got a drop in crack growth. But for Piarco soil, it was not like that.
Okay, thank you.
I have a question. Do I have any time left?
No, we have less than 1 second.
Oh, okay. Next time.
Yeah, next time.
You can email me.
Yeah, okay.
Oh, okay, sir. I will.
All right.
Okay, thank you, Dr. Birch.